We just calculated the kinetic energy of an electron that was going really fast. It was going almost a little over 1% the speed of light, extremely fast electron, and it was only 56 times 10 to the minus 19 joules. Not a lot of energy. There's a prefix for that. I think it's yocto. I think it would be 5,600 yoctojoules, some prefix that nobody uses, one of those Marx Brothers prefixes. I mean, it's irrelevant. You don't want to use prefixes down in the yocto, zeta, groucho thing. So what you want to do, we need a sort of atomic microscale unit of energy, and we have one. It's called the electron volt. The electron volt is confusing because it's so simple. Okay, so that's what I'm going to have to explain to you. So the electron volt, its definition, it's simply a microscopic unit of energy. Just like a joule. A joule is the macroscopic unit of energy. Electron volt is a microscopic unit. To really see it, what we need to do is go back to electrostatics for a minute. So let's imagine we have an electric field going this way, back to the electric field. That nice direct field. It's easy to think about, relative to the magnetic field at least. And remember, we could draw potential lines along this electric field. And now let's think about a coulomb of charge, the macroscopic amount of charge. Big whopping coulomb sitting right there. And let's think about an electron. Well, now let's make it a proton with a charge of 1e. Right? That's the macroscopic unit of coulombs. The microscopic unit is the elementary charge unit. So coulomb of charge and a proton with 1e of charge. Well, if you just let them go, they're going to fly this way. They're going to go along the field like that. So this must be a high potential, and that's a lower potential. So we're going to call this the 1 volt line and the 0 volt line. Right? If they make it from here to here, they've changed their electrostatic potential by 1 volt. It's gone down by 1 volt, and they've picked up a certain amount of kinetic energy. So we know how to calculate the energy when they get to here. The energy that they pick up would be the kinetic energy. It would just be the charge times the potential difference, right? It would be a coulomb times a volt. Right? It would be 1 CV, 1 coulomb volt, which is what a joule is, right? That's equal to a joule, okay? Now this particle with a charge just of E made this path. It lost some potential energy. It's going to gain kinetic energy. It's the same idea. It's just an electron times a volt. Okay? No, not an electron, an elementary charge unit times a volt. E times V. Or we also call it an EV. Okay? So it's direct. The reason it's sometimes confusing is because it's literally an electron times a volt. Just like a joule is a coulomb times a volt, we just don't give it a fancy name. We just call it an electron volt. So it's not a measure of charge. It's not a measure of potential. It's energy. The conversion factor also can be a little tricky because the conversion factor for joules and electron volts is exactly the same as for coulombs and elementary charge units. 1 EV is a teeny amount of energy. It's 1.6 times 10 to the minus 19 joules. Same conversion factor because they're both going over a volt. Just one of them is a coulomb and one of them is an electron. So sometimes when you do problems, you prefer to work in MKS units. But you may occasionally be given a problem where it's microscopic and done in EV. If you want to get back to MKS, maybe calculate a speed in meters per second, you got to convert it, but you've already memorized the conversion factor. It's the same as for elementary charge and coulomb.